Hey, this is Alex from Tutors and Friends, and today we're going to be looking at characteristics of quadratic functions. So if you remember what a quadratic function is, it's a type of polynomial where the highest degree term is x squared. And looking at our little graph right here, our sketch of a quadratic function, it's in the shape of an upside down parabola. And there's a couple of features we can point out about this parabola. Because this parabola is facing down, in this instant it has a maximum value, and that maximum value is also called the vertex of that function. Now remember, a parabola can also face upward, and if it were facing upward, it would have a minimum value, and that minimum value would also be the vertex. Parabolas have a symmetry about their center, and the axis around which they have symmetry we call the axis of symmetry. That axis of symmetry is always an x equals equation, and it's always whatever the x value of the vertex is. Okay, so if the vertex was at an x value of 2, the axis of symmetry would be x equals 2. A couple of other things, we've got x-intercepts on our function. Those are the points where the function crosses the x-axis. A parabola can have either one x-intercept, two x-intercepts, or no x-intercepts, okay? An example where it had one x-intercept would be where the vertex is also touching the x-axis. Two x-intercepts would be like our drawing in blue here, and no x-intercepts would be where the parabola is in a position where it'll never cross the x-axis. Now keep in mind, parabolas will also have a y-intercept where the function crosses the y-axis. Every parabola will always have every parabola will always have one and a maximum of one y-intercepts. Okay, so if you remember, we have a couple of different general forms in which we can algebraically describe a quadratic function. The first one is vertex form. Vertex form is a times x minus h quantity squared plus k. The vertex of a quadratic in this form is always given by the coordinate h comma k, where whatever the h value is, that's the x value, whatever k is, that's the y value of the vertex. And the axis of symmetry would always just be equal to x equals h, okay? In standard form, which is ax squared plus bx plus c, the vertex can be found by using this equation. The x value of the vertex would be equal to negative b over 2a. And to find the y value of the vertex, you would just plug that back into the function. So whatever negative b over 2a is, you just plug that in for x, and whatever you get out, that's the y value of the vertex. Now, b and a refer to these coefficients in our standard form. So a is whatever the number in front of x squared is, b is whatever the number in front of x is, and c is this constant value. Okay, so the vertex for a standard form would be negative b over 2a, comma, f of negative b over 2a. And the axis of symmetry would just be x equals negative b over 2a. And the last form we have is factored form. Factored form is really convenient for finding the x-intercepts of a quadratic. In order to find the axis of symmetry, you would take the two x-intercepts of the quadratic and you would find the average of them. Okay, so notice on our example in blue down here how our x-intercepts are right here, and exactly in the middle of those two things is the axis of symmetry. Okay, so if you ever need to find your axis of symmetry from factored form, you can first find the x-intercepts, and then you can just find exactly the middle x value between them, and that is the axis of symmetry. Once you find that x value, like standard form, you just plug that back in to figure out what your y value is for your vertex. Okay, so those three different forms, and those are some features of a quadratic. Let's look at our first example. This example wants us to graph the function and to label the vertex and the axis of symmetry. All right, so we've got our function f of x equals negative 1/4 times x plus 2 quantity squared plus 1. Great, so this is written in vertex form. And a couple things that I want to point out about this. We can see that our a value is negative, And if you recall, a negative a value means that this quadratic function is facing downward rather than up. Okay. Additionally, our a value is a fraction, which means that compared to the parent function, our quadratic that we're looking at is actually wider, right? Remember, a fractional a value means a wider function. All right, and then because this is in vertex form, it's very easy to find the vertex. The vertex is given by h comma k, where h in this case would be -2 and k would be +1. How am I getting those numbers? It's because it's x plus 2 inside the parentheses, and remember the h value is always the opposite of whatever the sign is in front of the number in the parentheses, and then the k value is just this 1 outside. And the axis of symmetry would just be x equals -2 because it's just the x value of the vertex. All right, awesome. Now, when we're sketching a graph, there's a few different ways to go about it, but when I have the vertex, what I like to do is take a couple of x values to the left of the vertex and a couple of x values to the right of the vertex, plug those into the function, and find the associated y value. So let's go ahead and do that now. So if our x value of our vertex, if our axis of symmetry is -2, two x values to the left of that would be -4 and -3. And two x values to the right of that would be -1 and 0. Okay, so we'll plug those into our function. When x is -1, we get -1/4 times, when x is -4, -4 plus 2 squared plus 1. -4 plus 2 is -2. -2 squared is 4. 4 times -1/4 is -1. And -1 plus 1 is 0. So when x is -4, f of x is 0. Great. Let's do that again for when x is -3. When x is -3, we get -3 plus 2 squared, -1/4 out front, plus 1. -3 plus 2 is -1. -1 squared is 1. 1 times -1/4 is -1/4. And that plus 1 is 3/4. Perfect. And then remember, there's a symmetry about this. So the two x values to the right of our of our axis of symmetry are also going to be the same y values. Just like that. Great. So now we'll go ahead and plot these points, starting with our vertex. So our vertex is -2, +1. And then our first point that we'll plot is -4, 0, -3, 3/4, -1, 3/4. I'm sorry, that's 3/4, perfect. And then 0, 0. Perfect. Great. And then it wants us to label our vertex and our axis of symmetry. So our vertex is right here. That's our vertex, and that's at -2, 1. And then our axis of symmetry is right here, AOS, and that's at x equals -2. Great. Awesome. Let's look at our next example. In these exercises, we want to use the axis of symmetry to match the equation with its graph. All right, no problem. So looking at number 15, y equals 2 times x minus 3 squared plus 1. Great, so this is in vertex form, so our axis of symmetry is whatever our h value is. In this case, our h value is 3 because of that -3 inside the parentheses, so our axis of symmetry would be x equals 3. Now all we need to do is look for one of the graphs where that is our axis of symmetry, and if you look here, it looks like graph C matches with that equation. So number 15 would be C. Doing the next thing, for number 16, we have y equals x plus 4 times quantity squared minus 2. In this case, our h value is -4 from that +4 inside parentheses, so x equals -4 would be our axis of symmetry. So for 16, the graph that has an axis of symmetry of -4 is D. We'll do the same thing for 17 and for 18. For 17, we've got y equals 1/2 times x plus 1 squared plus 3. In this case, our h value is -1, so our axis of symmetry is x equals -1. which matches up with graph B. And then via process of elimination, there's only one left. It has to be A for the last one. But we can verify that. We see that on 18, we have an H value of positive 2. So that means our axis of symmetry is x equals 2, just like you see on A. Okay, awesome. So from vertex form, it's very easy to identify the axis of symmetry. Next example, we have a standard form quadratic, and we want to graph it, and we want to label the axis of symmetry and the vertex. Okay, so check this out. We've got our standard form quadratic. How did I know it was in standard form? Because it's written in the form ax squared plus bx plus c. Okay, let's identify our a, b, and our c values. So our a value is 3, our b value is -6, and our c value is 4. Okay, and if you recall, to find the axis of symmetry for a quadratic in standard form, you just do x equals -b over 2a, which, plugging in our values we just found, that would be -6 over 2 times 3, which would be +6 over 6, which equals 1. So our axis of symmetry is x equals 1. Our axis of symmetry is also the x value of our vertex. So for our vertex, we'll put 1, comma, we don't know what the y value is yet. How do we go about finding the y value? We simply just plug that x value in back into the function. So f of 1 would be equal to 3 times 1 squared minus 6 times 1 plus 4, which is equal to 3 minus 6 plus 4, which is equal to -3 plus 4, which is 1. So our y value is also 1, meaning our vertex is at 1, comma 1. Now for this, you can go ahead and pick 2 x values to the left of the vertex and 2 x values to the right. But I'm actually going to show you a slightly different way to do this one using the x-intercepts. And so let's go ahead and do that now. We're actually going to factor our quadratic for this one. So let's get rid of our table here. Okay, so to factor our quadratic, we start by making a cross like this. And we'll take our a value and multiply it by our c value and put that up top right here. So 3 times 4 is 12. And then we'll put our b value down below, -6. Now, we're looking for 2 numbers that multiply to 12 but add to -6. And there may not be any 2. And if there are not any 2, we actually can't do this method. So hopefully there are 2. So what are some factors that multiply to 12? We have 3 and 4. That doesn't add to -6. We have -3 and -4, 6 and 2. It doesn't look like there are any 2 factors that are going to work for this. So we'll go ahead and do it our standard way with the table. And I'll show you factoring at the end of the video just so you can see that. So we'll make another table. X, f of x, we'll pick 2 x values to the left of the vertex. So -1, 0, 2 x values to the right, 2 and 3. When x is -1, we have 3 times -1 squared minus 6 times -1 plus 4, which is 3 plus 6 plus 4, which is 13. When x is 0, we have 4. When x is 2, we have 4. And when x is 3, we have 13. Great. All right, so we'll go ahead and start plotting those points. Starting with our vertex at 1, comma 1. Oh, let's fix our axes. Perfect. All right, 1, comma 1. Oh, that did not fix them. All right, 1, comma 1. 0, comma 4. 2, comma 4. 3, comma 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then -1, comma 13. Great, so there's our quadratic, nice and skinny. Remember, because the a value is greater than 1, in this case it's 3, it's facing upward, and it's skinny, okay? All right, great. So that's how you do that, remembering that our equation to find the axis of symmetry is negative b over 2a, and then to find the y value, you just plug that number back into the function. All right, so this next example wants us to find the minimum or the maximum of this function, describe the domain and range, and where f of x is increasing or decreasing. Okay, so we've got a lot going on in this. So let's go ahead and do this problem. So first thing we want to figure out is whether this has a maximum or a minimum. You can see this function has a negative a value because of this negative 1 out front of x squared, which means that it's going to face down, which means that it has a maximum value right there at the vertex. So to find that maximum value, we just figure out what the vertex is. And remember, we just do negative b over 2a, which in this case would be negative 4 over 2 times negative 1, which would be negative 2. So that's our x value of our vertex. To find the y value, we just plug that back into the function. F of negative 2 would be negative 4 plus 8, which is 4, minus 2, which is 2. So our maximum value here is negative 2, 2. Great. The domain of every quadratic function, meaning the span of x values or the distance it goes from the left of the graph to the right of the graph, is always the same. The domain of every quadratic is always negative infinity to positive infinity. Okay? The range of a quadratic is the only thing that changes. The range is either, do a quick little sketch, either from its minimum value up to infinity, if it's facing upward, or it's from its maximum value down to negative infinity, if it's facing downward. So in this case, since we have a quadratic that's facing downward, it's going to have a range of anything from 2 to negative infinity. And notice how I put a bracket around the 2, meaning that the range can be equal to 2, rather than a parenthesis there. Great. Now, this function, let's do a quick little sketch of it. We know the vertex is at negative 2, 2, so something like that. And we'll pretend it looks like that. It's asking, where is it increasing or decreasing? Okay, so it's increasing as you go this way. So you always read from left to right. And from left to right, it's increasing right here. Once you get to the vertex, it starts decreasing. Okay, so we would say that it's increasing. Let me give myself some more space. We would say that it's increasing from negative infinity to negative 2, and that it's decreasing from negative 2 to infinity. Okay, it's increasing from x equals negative infinity up to x equals negative 2, like that, and then it's decreasing from negative 2 over to positive infinity. All right, great. So on your own, go ahead and try this second one, 2x squared minus 12x. Hopefully it makes sense. And let's take a look at this example here. So this is a real-life application of a quadratic. The path of a diver is modeled by the function negative 9x squared plus 9x plus 1, where f of x is the height of the diver in meters above the water, and x is the horizontal distance in meters from the end of the diving board. What is the height of the diving board? What is the maximum height of the diver? Describe where the diver is ascending and where the diver is descending. Okay, so oftentimes with these real-life quadratic problems, one of the best things you can do first is sketch a graph. So let's rewrite our function. Negative 9x squared plus 9x plus 1. All right, so let's first figure out what our vertex is. Okay, so the x value of our vertex would be negative b over 2a, which would be negative 9 over 2 times negative 9, which would just be equal to positive 1/2. And then our y value of our vertex would just be f of 1/2, which is negative 9 times 1/2 squared plus 9 times 1/2 plus 1, which is negative 9 over 4 plus 9 over 2, which is really 18 over 4, plus 4 over 4, which is really 1. And so that's equal to 9 over 4 plus 4 over 4, which is 13 over 4. So now we know that our vertex is at 1/2, comma 13 over 4. Great. Get rid of this so I have some room. All right, now let's do a quick sketch of our situation here in our function. Draw a set of axes. Okay, where x is the distance from the end of the diving board, and f of x is the meters above the water, the height above the water. Okay, so let's plot our vertex over 1/2 up 13 over 4, which is really 3.25, 3 1/4. Vertex is right there. And then our y-intercept is at f of 0, which if you plug in 0 for x, you get 1. The y-intercept of a quadratic in standard form is always whatever the c value is, okay? So our y-intercept would be right here. And then we'll we'll figure out another point when x is equal to positive 1, f of 1. X would be equal to, f of x would be equal to also 1. Okay, so our graph kind of looks like this. Now, the function asks us, what is the height of the diving board? In this context, the height of the diving board would be whatever the whatever the y-intercept of the function is. And in this case, that's 1. So the height of the diving board would be at 1 meter. So the answer to A is 1 meter. Part B asks, what is the maximum height of the diver? Well, this purple graph that we just drew models the maximum height of the diver, or models the height of the diver over distance. And the maximum height would be whatever the vertex of this quadratic is, which we already found was 1/2, comma 13 over 4. So that means that the maximum height of the diver is 13 over 4 meters, or whatever the y value of the vertex is. Okay. And C, describe where the diver is ascending and where the diver is descending. Okay. So the diver is ascending anywhere from 0 feet away from the diving board up to, 0 meters away from the diving board up to 1/2 meter away from the diving board. Okay? And that would be where the function is increasing. That would be where the diver is ascending. The diver is descending anywhere from the maximum outward, away from the diving board. So that would be where the function is decreasing. So we could say that the diver is ascending from 0 to 1/2, and the diver is descending from 1/2 up till he hits the water, which we should probably figure out where does he hit the water. And to figure out where this diver hits the water, we'll want to find the x-intercept of this quadratic. So let's go ahead and do that now. So f of x is equal to negative 9x squared plus 9x plus 1. So this function is not factorable, so we'll go ahead and use a different method called the quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And we'll plug in our values. X equals negative 9 plus or minus the square root of 81 minus 4 times a times c, which would be plus 36 all over negative 18. So that means our x-intercepts are negative 9 plus or minus 81 plus 36 is 117, square root of 117, all over negative 18. Let me go ahead and do that on a calculator. So square root of 117 is 10.8, so negative 9 plus or minus 10.8 over negative 18. And we'll get a an x-intercept of 1.1. So 1.1 meters away from the diving board is where the swimmer hits the ground. Sorry, the water. Great.